Welcome. In this session, we'll learn the different Fourier representations. So let's start. Now, in the previous session, we learned what is the fundamental concept of Fourier analysis and why are we using sinusoids. Now, we know the signal can be either continuous time signal or discrete time signal. So based on the nature of this signal, is what's the time nature of the signal, whether it is a continuous time or discrete time. We will have a one Fourier representation. Means if it's continuous, we'll have one Fourier representation, and if it is discrete, we'll have another Fourier representation. In short, we'll use continuous time sinusoids here, and we'll use discrete time sinusoids here, right? Now, same way as signal can be, this continuous time signal can be periodic. So based on the periodicity or aperiodic, we have different Fourier representation for this. So based on the nature, means whether the signal is periodic or aperiodic, we have another representation of this Fourier. So if the signal is periodic and continuous, we'll have one Fourier representation. Same way, if the signal is aperiodic and continuous, we have one Fourier representation. If it is periodic but discrete, we have another Fourier representation. And if it is aperiodic but discrete, we have another Fourier representation. Now, before I proceed, please remember to distinguish between the continuous time signal and sinusoids. In short, we'll use omega. Omega denotes the continuous time signal frequency or the sinusoid frequency, and this small omega means the discrete time sinusoid frequency. All right. Now, if it is continuous and periodic, the representation is simply said as Fourier series. So we use Fourier series for these signals. If it is continuous but aperiodic, the Fourier representation is called Fourier Transform. Same way, if it is discrete but periodic, it is referred as discrete time Fourier series. If it is discrete but aperiodic, it is referred as discrete time Fourier transform. Right? So this is based on this, we have four representations of this Fourier. So based on each of the same, whether it is time, whether it is discrete time or continuous time, we have one class of signals. Another class is based on whether the signal is periodic or aperiodic. If it is continuous, it can be periodic or aperiodic. If it is discrete, it can be periodic or aperiodic. And based on this, we have different representations of this Fourier. So now, before I tell you what are these four different Fourier representations for these different class of signals, please remember that we can use these sinusoids. We can use this real sinusoid or cos wave, or sometimes we use both, means sine omega t plus cos omega t to x plus to represent our x of t or x of n. So here we will have omega n or omega or cos omega n. Or we can also use e raised power j omega t or e raised power j omega t. So that's a continuous time signal, we'll use these. If it's a discrete time signal, we'll use j omega n or e raised power j omega n. Okay. Sorry, this e raised power j omega t if it is a continuous time signal. Use it j omega. It's a discrete time signal. So we can use these, and we know this is equal to e raised power j omega t is simply as cos omega t plus j sine omega. So we can either express x of t or x of n as a weighted sum of these cosine or sine waves, or using both sine and cos waves, or we can use complex sinusoids. That's the point I'm making here. And based on this, we have different representations of this Fourier, and that are referred as, for example, some the Fourier series representation, complex Fourier series representations, this trigonometric Fourier series representation. So based on that, we have different representations of this Fourier analysis. Now in this class and in the sessions that will follow, we'll use e raised power j omega n, or if it's a discrete time sinusoid, or j omega t if it's a continuous time signal, right? So we'll express x of t as a weighted sum of this complex sinusoid, or we'll express x of n as a weighted sum of this complex discrete sinusoid. That's the point I'm making. Remember that. All right. Now, when we express, remember from the previous session, if you remember x of t, we express it this like this: a1 sine omega 1 t plus a2 sine omega 2t plus a3 sine omega 3t plus so on. When we do this, simply write it like this: summation ai sine omega I t, and summation is 1 over I. When we do this, our goal is not to determine omega 1, omega 2, and omega 3. Our goal is to determine a1, a2, and a3. Means what is the value of this a1 and a2 and a3. Now, why are we doing this? Now, to illustrate this, we have already done it for the side, for a sine wave, for a square wave. The representation is something like this: plus 4 by 5 pi sine 5 omega t plus so on. Let's say that the square wave has only odd frequency components. Now omega will be some value, 3 omega will become some value, and 5 omega will be some value, right? So our goal is not to determine omega, our goal was to determine what is this quotient. What is this quotient, or what is this quotient? In other words, how much content of omega is contained in that x of t. Same way, how much content of 3 omega is contained in that signal. How much content of 5 omega is contained in that signal. That's why our goal is to determine the coefficients. How much is the coefficient, means how much is the content of that frequency, of that sinusoid contained in that signal. So our goal in Fourier analysis is to determine these coefficients. Right? See, if we have x of t is the given signal, and we want to see the Fourier analysis of this, means if we say this Fourier, our goal is to express it like this. So ai sine omega I t. Our goal is to determine ai. How much ai? I mean, ai will tell us how much content of omega I is contained in it. And this is referred as Fourier answer. So the goal in Fourier series or Fourier transform is to determine how much is this AI. And how do we do that? That's referred as the Fourier representation. And this is referred as the Fourier representation. Now to illustrate this, let me show you the different these four Fourier representations. What is Fourier series? What is Fourier transform representation? What is discrete time Fourier series representation? What is discrete time Fourier representation? All right, let me, so based on the class or the nature of the signal, we have two classes of signals. One is continuous, so one is continuous, another is discrete. So this signal can be continuous or discrete, right? And based on whether the periodicity nature, means whether the signal is periodic or aperiodic. Based on this, we have another class of this Fourier representation. Now, if the signal is continuous and periodic, this is referred as Fourier series. We already saw it is referred as Fourier series. And the Fourier representation is simply referred as Fourier series, and the representation is like this. Our goal is to express x of t as a weighted sum of sinusoids, and this time we are using complex sinusoids. Remember that we are going to use these sinusoids. So our goal is to express x of t as a weighted sum of sinusoids. Weighted sum of sinusoid. Now I'm using x of k here. Please don't be afraid. This means the coefficient. This means that a1, a2, a3. Please don't be afraid of this. So the summation is running over k. K can go from minus infinity to plus infinity. E raised power j omega, sorry, k omega, it should be, let me use k on the right side, and this is that. And let us call it omega naught. For Fourier series, let us call it omega naught. Now this means this is the periodic signal. Now what is this x of k? X of k is the Fourier frequency representation. Means what is x of k? X of k is given by 1 by t integral x of t e raised power minus j omega naught kt. What is omega naught? Omega naught is simply 2 pi by t, because this is a periodic signal. Because this is a periodic signal, it will be like this. Now please don't be afraid of this x of k. It means simply the coefficient. What's this coefficient? And when you determine x of k, it tells you how much content of this complex sinusoid is contained in that signal. All right, when you determine this. Now, if it is continuous but aperiodic, this is referred as Fourier transform. So this is the Fourier representation is referred as Fourier transform, and the representation is, if it is x of t, we say it's like 1 by 2 pi minus infinity infinity x of, sorry, this would be coefficient. What is this coefficient? Let me call it x of omega e raised power j omega t d omega. Wire. What is, again, what is this integral? Integral means sum. You know, integration means simply summation. Means this means simply taking the sum of all the complex sinusoids with some coefficient. And what's this coefficient? This is referred as the Fourier frequency representation, and this is called the Fourier transform. E raised power minus j omega t dt. Please don't be afraid of these integrals and summations. You have already seen this. This is referred as the Fourier transform. And this is actually referred as the Fourier transform. You might have already seen. And this is referred as the inverse Fourier transform. Please don't be afraid of these. The signal is continuous, and you are expressing it as a weighted sum of complex sinusoids. The representation is simple. And this is referred as Fourier transform. Don't be afraid of this. So this is the Fourier transform. This is the inverse Fourier transform there. Right? So we are expressing x of t as a weighted sum of these complex sinusoids. That's the main literal meaning of this. Now, if it is discrete but periodic, then this is referred as discrete time Fourier series. The Fourier representation is referred as discrete time Fourier series. All right. And what is the representation? Means what is the, we are going to use a different omega. Now this is x of n. X of n is a discrete time signal, and the representation is like this. The representation is x of k e raised power j k omega n, where again this is a coefficient. What is this coefficient equal? X of k is simply 1 by n summation x of n e raised power minus j k omega naught. What is this omega naught? Omega naught is again 2 pi by n. This is a periodic sequence, so it will have some period. Right? So this is the discrete time Fourier series. Now, if it is discrete but aperiodic signal, then this is referred as discrete time Fourier transform. Fourier transform. So this is referred as discrete time Fourier transform, and the representation is like this. X of n is given by this. This is 1 by 2 pi minus pi to pi. If you remember, the maximum frequency or the frequency variation of a discrete time signal is from this minus pi to it is, sorry, this is different omega, should use x omega, e raised power j j omega n d omega, while again this is the coefficient. This coefficient so omega is given by this summation, n is running from minus infinity to plus infinity, x of n e raised power minus j omega. So these are the four Fourier representations. Please don't be afraid of this. The fundamental concept is same. Means we can express any x of t or x of n as a weighted sum of sinusoids. And this time the sinusoids we are using are complex sinusoids. Means we are using e raised power j omega t or e raised power j omega n. That's the sinusoids. Please don't be afraid of this. Now here the coefficient of these sinusoids is x of k, represented by x of k. Here the coefficient is x of omega. Here the coefficient is x of k again, and here the coefficient is x of omega. That's how we express these. These are simply the coefficient, don't be afraid of. Now one important point, please pay attention to this. Here the coefficient is 1 by t and it is with this integral. Here the coefficient is 1 by 2 pi, and it is with this integral, means inverse Fourier transform. Here the coefficient is 1 by n, and here the coefficient is 1 by 2 pi. And remember, you can interchange these, means you can write this 1 by t with this also. There is no hard and fast thing. So if you see the representation that 1 by t is written here, don't worry about this, you can also do that. Or you can even do this like this, 1 by under root t here, 1 by under root t here. Same way, you can write this 1 by n also here. You can also write it here. So there is no hard and fast rule that whether you should use this constant with this or this. So it has no impact on the representation. Same way 1 by 2 pi can be written here also. Or you can write it 1 by under root 2 pi here and 1 by under root 2 pi here. So the scaling constants, these are for that. The scaling constant can be put on either of the representation. Now, please pay attention, very, very important point. Now, this is the time domain representation, means you can express x of t as a weighted sum of the sinusoids, and the sinusoids we are using are complex sinusoids. And this x of omega is the coefficient. Now, whether I say, please remember that whether I say x of t or x of omega, or this x of n or x of omega, this is very, very important point. This is the time domain representation of the signal. This is the frequency domain representation of the signal. This is the time domain representation of the discrete time signal. This is the frequency domain representation of the signal. Whether I say x of t or x of omega n, or this x of n or x of the small omega, it means one and the same. It means I'm talking about the same. This is the time domain representation. This is the frequency domain representation. This is very, very important point. Please remember this. So whether I say x of t or x of omega, I'm talking about the same information. As a communication engineer, we are talking about the same signal. So as a communication engineer, we are talking about the same signal. Whether I say x of t or x of omega, I'm talking about one and the same thing. But the representations are in different domains. Means x of t is in the time domain, x of omega is in the frequency, x of capital omega is in the frequency domain. Same way, if I say x of n or x of small omega, it means one and the same thing. I'm talking about the same thing. X of n is the time domain representation, x of small omega is the frequency domain representation. Whether I say this one or this one, I'm talking about the same thing. It means only the representations are different. And what's the fundamental concept of Fourier? Expressing x of t or x of n as a weighted sum of sinusoids. And the sinusoids we have used here are complex sinusoids. I hope you have got this idea of what is Fourier analysis, what's it all about, and why we go for sinusoids, and why we express x of t or x of n as a weighted sum of these sinusoids. What is the concept behind that? I hope that's clear. Now, in this session or in digital signal processing, we will start with this. We will start with You might have studied already these in signal systems class, or in communication class, or in maths class. But we'll start with this one. We'll start with this. How do we get the frequency domain representation if x of n is given? That is our next session. So in the next session, if x of n is given, how do you obtain x of n? So this is given. How do you obtain x of n? And we'll start with this discrete time Fourier transform. Remember, I haven't used here the summation running is k. Here the summation running is n. I haven't told you the duration on this. Please pay attention. I haven't given you that. This will be clear when we do a discrete Fourier transform. All right. So let me end this session here. I hope you have got the idea what are the different Fourier representations. Remember that Fourier representation might change if you use these. Please remember that if you use directly these, where are these? Sine and cosine. The Fourier representation may look different to you. So don't worry about it. The fundamental concept is same. Only difference is we have used a different sinusoid. Different sinusoid means we have used a complex sinusoid. And one more thing, the coefficients, meaning the scaling constant, can be with either of the two. Means it can be with x of t or x of t. It depends. The same way, it can 1 by 2 pi can be with x of t or x of capital omega. It can be with either representation. So don't worry about it. It's a scaling constant. You can put it on either representation. All right, let me end the session here. In the next session, we will start with the discrete time Fourier